Okay, off we go. So here's where we're picking up from last time. So new section, we're starting with 2.3, talk about derivatives. Here's the first big headline. A huge difference between single variable calculus and multivariable calculus is that in single variable calculus there's really only one kind of derivative. It's the derivative. There's nothing else to say. I mean, you can talk about higher derivative, but in terms of first order derivatives, just the one. That's all there is. This is not the case with multivariable calculus. There's a bunch of different kinds of derivatives that relate to each other in various different ways. But there is no single thing. So heads up for that. Now, why do we use the term derivative to describe a bunch of things that are in fact different? And the reason is because every kind of derivative we're going to talk about has this common unifying feature, and that is in their ways they relate input changes to output changes. So this is a big common theme to look for. Every derivative that we're going to write down in its way will be a relationship between input changes and output changes. And please be on the lookout for how in their different ways they all do this. Okay, now I am going to start with partial derivatives. For a bunch of reasons that are somewhat sympathetic, but frankly, this is something I struggle with. I don't really like starting with partial derivatives, and I'll tell you why in just a moment. But here's why we do. It turns out they're really easy to compute. That's nice, and it's kind of, it's good to get a win into the win column, right, when we're just getting started with things, and that's nice. They are relatable. That's kind of nice, but there is a double-edged sword here. There's something unfortunate about partial derivatives being relatable. It reinforces what could be argued to be a bad point of view. So I'm going to leave that as a dangling thought, and we'll be able to come back and address that better after we've seen what the other options are. And then what really is the deciding factor is that the book does it this way, and I can deviate from the book, but every time I deviate from the book, there's kind of a cost of confusion, and I don't feel so strongly about this that I feel it's quite worth that cost. Okay, so with that said, I do want to give you a warning, and that is, ultimately, the best way to think about multivariable derivatives is not this. We're starting with partial derivatives for these other reasons, but not because they're fundamentally deep down how you should think about multivariable derivatives. They're not, in my opinion. Just an opinion. Okay, so we will talk pretty soon, probably Monday, I think, about what I think really is the best, most natural, most fundamental. If you could only remember 4 things from this class, one of them would be how should you think about multivariable derivatives and what should that be? That'll be coming on Monday. Okay, all right, so let's do it. I'm going to describe what the process is for computing this thing called a partial derivative. And then we'll do some examples. And then we'll take it from there. So anyway, the process is this. You've got this multivariable function. You've got a bunch of different variables. Just decide that you're going to view most of them being constants. Just pretend that they're constants. It's kind of bogus if you really think about it. They're not constants, but we're going to choose to view them that way. A little sketchy. Right? But anyway, that's the first step. One of them, of course, we do have to leave as being a variable. Otherwise, there's nothing interesting to happen. So we're going to take a multivariable function and effectively turn it into a single variable function by viewing it as only one of those variables is actually going to behave as a variable. And so now that you've got a single variable function, okay, we know how to take derivatives of single variable functions. So just do it. Just go ahead. So that's our process. Now, I hope you're a little suspicious. I hope you're kind of wondering to yourself, hey, can you do that? And why would I care about what we get that comes from cheating? Right? I mean, this should be fishy, right? We will come back and address that in a minute. For the moment, let's just do it. So some notations we need to talk about. Here's how we typically write a partial derivative. Do be careful. This symbol right here, that symbol is not a D. D would mean something different. D would suggest you're taking literally a single variable derivative of something that is literally not a single variable function. You can't do it. It doesn't make sense. It's not okay, right? So if you're going to indicate partial derivative, you've got to make this little symbol, and you're going to have to fight that urge to bring this loop all the way back down to the bottom to make it a D. You're going to want to make it a D. You can't make it a D. Okay. All right. Likewise, it's not a lowercase Greek letter delta. That's just not. Right, so be careful of that as well. Okay, so that's one of the most common notations. The other notation I'll talk about is this right here. This is kind of vaguely Newton-like notation, right? It's like with the prime, right? Except, of course, now again, I can't just say prime. There's a bunch of different variables that I could choose to be the variable that I keep viewing as a variable. So I've got to indicate which variable I'm taking the partial with respect to. So this notation has its moments of being extremely convenient. We will see some of those a little bit later on, a few weeks from now. I don't know, a week or two, I lose track of time. Sometime soonish we will see a situation where this is super handy. But most of the time, I think that Leibniz notation is a little bit better. It's a little bit more satisfying somehow. Okay. All right, example. This looks like a hard one. Look at that function we're going to take a partial derivative of. It's a product of three factors. One of them is a composition. There's cotangent. There's exponentials. Yikes. Looks like a hard function. This is actually a really easy partial derivative to compute, which makes it a fantastic starter example. And let me remind you of the process. It says right here we're taking a partial with respect to y. The very first thing you do when you take a partial derivative is you set all the other variables equal to constants. So x, being one of the other variables, is a constant. That means e to the x is a constant. It means that x is a constant. That means x squared is a constant. Oh, by the way, z also is one of the other variables. So z is a constant. So e to the z is a constant. So all of this is a great, big, ugly constant. So this is not we're taking a derivative of a nasty product of multiple factors. No, we are taking a partial derivative. Let me just say it bluntly. We're taking a derivative with respect to y of constant times y squared. And that's super easy, right? Multiplicative constant times y squared. Derivative of y squared with respect to y is 2y, and the constants come along for the ride. That's how multiplicative constants work. Everybody remember all their single variable calculus? Is that all good? Okay, so done, right? It's really easy. I like to nominate partial derivatives as being the easiest derivatives to compute. Because not only do you get to use all of your old tricks from single variable I don't know why it does this. I didn't touch it. It just switched the input there. Does somebody have a clicker somewhere in the audience? And I don't know. This has been happening to me all day. Anyway, not only do I get to use all my old rules about, product rule, quotient rule, power rule, chain rule, all of our old friends, right? Still works just fine. I also get to just treat a bunch of my expression as being a constant. Isn't that awesome, right? It makes life a lot easier. So, super easy to compute. All right. Couple more examples. These are just a couple of quickies, just because they look weird. Here, let's take this x partial of this function right here, and that looks like a hard one. It looks like function to the power of a function. It's not, because y in this case is a constant. That means that my exponent is a constant, and when you have an expression to the power of a constant, right? Chain rule, power rule. So old single variable calculus, it feels weird to do it right? It feels weird to take that exponent and bring it down and subtract 1 when it looks like a function. It seems really wrong, but that's actually completely right. Everybody good? Other example is morally kind of equivalent. Again, it looks like a hard one, but don't forget partial with respect to z means the other variables are constant. So x is a constant, y is a constant. That means this whole base is just a constant. This is, in fact, nothing more than constant to the power of z. It's just an exponential. And I hope y'all remember all your old rules for derivatives of various, pat forms of functions. And this is how you take the derivatives of exponentials. Make sure you're good with all of these kind of old rules. Calc 1 is in the prerequisite trail of this class, right? So make sure that you're good with all of that. Okay, and now we come back to the big question, which is, look, I arbitrarily made a rule about how to compute this construction. I pulled it out of thin air with an obviously selfish motivation of convenience. Very suspicious, right? It's not at all clear that just because I wrote this down just to make it easy, that it actually means anything natural, right? And again, you can define whatever you want to define, but it then is your responsibility to show that it actually means something, that it's actually natural somehow, that it relates to the real world in some way. And I have not done that for y'all yet, right? This is a made-up, highly suspicious construction that is, as far as y'all know so far, is meaningless nonsense. Okay, so let me try to persuade you that this is not meaningless nonsense. There is a geometric interpretation we're going to talk about. There's actually several geometric interpretations we're going to talk about. I remind y'all have heard me give this speech a bunch of times, so I'll be quick with it, but calculus looks different depending on what kind of constructions you're looking at. If you're looking at a graph, well, that's one thing, but you might not be. You might be looking at level sets. You might be looking at the sort of the literal picture that I described. You might be looking at a parameterization. But there's a bunch of different pictures that you might be looking at, and okay, we're going to have to make sense now out of what does this partial derivative look like, depending on which kind of pictures we're looking at. So do keep that in mind. I'll remind you that the big idea here is we're going to have a bunch of different answers to the question, what do partial derivatives look like? And you've got to have partitions in your mind. And what calculus looks like in the context of graphs is a whole separate story from what calculus looks like in the context of level sets, which is different from what it looks like when you're looking at the literal picture, etc. Okay, so full warning. We're going to start off looking at graphs. You can see right here I'm looking at a graph of this function f. 2 variables in, 1 variable out, and there's our usual picture graph of a function of 2 variables. In that picture, I now want to ask the question, at some point a comma b down here in the domain, if I wanted to talk about the partial derivative of f with respect to y, where does that show up in this picture? How do I geometrically interpret this partial derivative of the function whose graph is this at this point a comma b? Okay, so the way we're going to answer this question is to think about how y partials are defined. It's defined in a 2-step process. Turns out both of those steps have natural, easy geometric interpretations, and here we go. So step 1, when you're taking a y partial, is to fix the other variables. X is my only other variable. So I'm just going to say x is not allowed to change. Now keep in mind, at the point in question, x is a. So if x starts off with value a and it's not allowed to change, that means x must stay specifically this value a. Yeah?
Could you please repeat the question you should answer?
Yeah, what do partial derivatives look like in the graph context? Yeah, that's right. So we're looking at a graph and we're trying to make sense out of what does a partial with respect to y look like. Yeah. Okay, so setting x equal to a, of course that gives us a plane. Right? So get a plane like that. And if we are going to restrict our attention to what's happening in this plane, we started off with a surface. Effectively, we're taking a cross-section, this vertical cross, I mean, this is a vertical plane. We're taking a vertical cross-section of our initially graph surface, and that cross-section then is going to be now just a curve. Right, so the very first step of defining a partial derivative, setting the other variables equal to a constant, gives us a curve. Okay, now another thing I want to point out, keep in mind we're taking a partial in the y direction. That's why we set x equal to a constant. Notice that when x is equal to a constant, that has my plane pointing in the y direction. And it's a little confusing, right? That, the plane x equals a points in the y direction. If you think about it just kind of semantically, it's confusing. So don't think about it that way, right? Think about it in terms of the geometry. Everything makes sense in terms of the geometry. Make sure that you see and rely on the pictures here. Okay. All right, now step 2. Step 2 when you're doing a partial derivative is to take your resulting single variable function, right? So now we're looking here at this cross-section curve. This is the graph. Oh, yeah, question.
I didn't see how the cross-section is in the y direction.
You don't see what now?
How the cross-section is in the y direction.
Okay, so we're setting x equal to a. So a is the fixed value of x, and x isn't allowed to change, and this is what that plane looks like. That's x equals a.
Yeah.
Right? And so notice that means, this plane is, on the one hand, it's vertical, but the other way to describe the direction that this plane is pointing is it is pointing in the y direction.
So we can say that it's pointing in the y direction like horizontally. Because vertically it's pointing the x.
Yeah, sure. Right. Yep, yeah. So among all vertical planes, this is the vertical plane that's pointing in the y direction.
Okay.
Yep, sure. Yeah. Okay, so we've got this single variable function. This is the cross-section of the graph of the initial multivariable function. This is actually the graph, then, of our resulting single variable function. And when I take the derivative with respect to y, derivatives are slopes of graphs. So I'm literally going to get the slope of the curve that is the cross-section of our original graph. And we can summarize this very pithily right here. The y partial is the slope of the tangent line, just like I've got it drawn there. Slope of the tangent line. Now, very importantly, slope of the tangent line to the graph. And I feel like this has to get hit hard, right? I've got to remind you periodically, this is when we're looking at graphs. This only makes sense in the context of graphs. As we go in the y direction, because that's the direction of our cross-section. So nice little summary. I think that this is highly relatable to single variable calculus. In single variable calculus, derivatives are slopes of graphs. Partial derivatives in multivariable calculus, they're slopes of graphs. You just have to say asterisk in the direction of the variable that you're taking the partial derivative with respect to. Okay. All right. Oh, is that a...
Yeah,
okay.
Good question.
Yeah.
So because we're taking the derivative with respect to y, like that makes sense to hold x as a constant.
Yep.
What role does the cross-section play?
Yeah, the cross-section is the geometric manifestation of setting x be equal to a constant.
Okay.
Yeah, is that cool? Because x equals a constant is that plane.
Okay.
Yeah. Yep. All right. So now here's an exercise for y'all. I think this is a really good exercise. We've already talked through this result right here. We drew some pictures. We made some arguments, right? Think through mathematically, geometrically, this interpretation of the x partial. Now, if you look at this kind of semantically, this is exactly what you would expect, right? Sure seems like it ought to be this, right? But that's not a mathematical argument. So I think it is a healthy exercise to think about how would the argument change if you wanted to argue about the x partial instead of the y partial, right? Can you make that argument, draw the corresponding pictures, and just make sure to check all the details, right? And make sure that this works also in the x direction. Really healthy exercise. Obviously, of course, as always, if you get stuck on any of that, come talk to me in office hours. I'll be very happy to walk you through it. Okay.
So in this case, we do hold like some b constant in this case?
Yeah, that's right. Well, so x is the variable, so you'd hold y constant, and that would be the value b. That's right.
That's
Yeah.
also
Yep, gives you a plane. Yeah, so go through the argument. Yeah, if you get stuck, let me know.
okay.
Right. Yeah, absolutely. Okay, that was for graphs. Again, we're going to get a totally different interpretation when we're looking at what is in fact a totally different kind of picture, right? So here we're going to entertain this kind of a function, 3 variables in, 1 variable out. Graph is not an option. Graph would be 4-dimensional. Can't do it, can't even fake it. Right? So, okay, but what I can do is I can draw this literal picture, what I like to call the literal picture. That being where I just very literally, R3, okay, there's R3. Right? And, so my target is R, okay, cool, there's my target, it's R. Right? I'm just literally drawing exactly what's happening. So in this context, what does a partial derivative look like? Okay, well, we're looking at this point, ABC. We're taking a partial with respect to y. That means y remains a variable. That means x and z are both constant. That means x has to stay a and z has to stay c, which is a couple of planes. Right? X has to stay at the value A and Z has to stay at the value C. And between the two of those requirements, that gives me this line. And conveniently, that line points in the direction of what is in fact the remaining variable, right? Y is allowed to change. And so, okay, that gray line there, X and Z being fixed means Y is what's allowed to change. And so I go in the Y direction. Alrighty. And okay, now let me remind you of an old fact from single variable calculus. In single variable calculus, a derivative is a factor. It's what you multiply by input change to get output change. Right? I hope you all remember that point of view about single variable derivatives. It's a factor that multiplies by input changes to get output changes, and that's exactly how we're going to interpret it here. If you change the input to the function by some amount, dy, in other words, if you move as allowed along this gray line, namely in the y direction, if you move by some amount, which of course we can actually call dy, that input change, you multiply by the derivative and you get the corresponding output change, which I'm going to call df, because it's literally telling us how much f is changing. So in this picture then, where in this picture is the partial derivative? And I'm sorry to say, it's itself not literally in the picture. That's the disappointment here. And you can't see the partial derivative. What you can do is see the job that it does, right? It's the thing that you multiply by input change in the y direction to get the corresponding output change that results. It's the factor. Is that cool? It's definitely not a slope, right? Nor should it be, because this isn't a graph. All right. Now there's another kind of picture we'll try to make sense out of. Let's go over to, why am I erasing that? That can just stay there. Let's think about level sets. And again, totally different kind of picture. Completely different kind of picture. This one's a little dangerous, by the way. There's a little bit of a landmine here. Notice that level sets are curves in this case. This is a level sets of a function from R2 to R1. And let's look at this level set right there. And level set's a curve. We're interested in a derivative. But it's really tempting from single variable calculus to just think, all right, well, I've got a curve. I want to take a derivative. Isn't that like the slope or something? Right? Because again, we've all had it drilled into us from the day one of Calc 1. That derivative is the slope of the curve. Right? And they're real sloppy about how they say that in a lot of single variable calculus classes. So you got to resist that temptation. We are not looking at graphs, so you can't just assume that derivatives are slopes. They aren't. We're not looking at graphs. We're looking at level sets. Completely different context. Right? So try not to step on that landmine. Here's how I like to think about this myself. Whenever I'm looking at level sets, I find it very helpful to imagine that the level sets are contour lines of a topographical map showing where I'm going on a hike. Right? And so if I'm going to make sense out of a partial derivative here, I think to myself, okay, that's me right there. That little dot is me. And I know if I want to take a partial with respect to x, that means I'll be moving in the x direction. And now, rhetorical question, as I move in the x direction, as I go that way, what kind of a hike am I going to have? What kind of experience am I going to have hiking there? And I got to tell you, I'm scared of this hike. I'm crossing contour lines fast. Yeah, this would be a really steep hike. That, you might say differently, that means that the graph of the function, where here I'm looking at the level sets, right? But what the graph would be, if I had a graph, which I don't, but if I had a graph, it would be a steep graph. That means that this would be a high value of the x partial.
Is it like the magnitude?
Is it like the what?
The magnitude of the derivative would be large, or?
Yeah, that's true. The unfortunate thing about level sets is you can't really tell from this picture whether you're going uphill or downhill, right? So that's annoying. So you're right. The magnitude, but maybe that's why I wrote large instead of, highly positive. Yeah, it could be negative, but it's not going to be close to zero. It's going to be a big number, not a small number. Yeah.
Is it the distance between the lines that says?
Yeah,
That's right.
That's right. I'm crossing contour lines fast as I walk this way, so that means steep. That means high value of the partial derivative. Yeah. Now, by comparison, let's think about what happens if I move in the y direction. If I move in the y direction, there's me walking in the y direction, and sure, I'm still crossing contour lines, but I get a lot more horizontal distance as I'm moving north. Right? I cross the same contour lines, but over a much greater distance, which means it's not as steep, which means it's a gentler hike, which means the slope is smaller, which means that the partial derivative is going to be small. Maybe plus, maybe minus. Again, you never know which. Level sets don't show values very often, but it's going to be smaller than the x partial. Yeah.
So you're talking about the distance of the point. If you're looking at it just like the point, right? You're talking about the distance from one level set to the next level set in relation to that point.
Yep.
So.
Yeah, that's right.
Okay, that makes sense.
Yeah, that's right. So as I'm going in the x direction, I gain 40 feet of altitude over that much distance on the map, which is super steep. Here I'm gaining the same 40 feet of altitude, but over a much greater distance. Yeah, that's right.
So you don't need the other two lines on the outside. You just need.
Yeah.
You just need
Well,
to-
man, I mean, all of this is kind of eyeballing, right? We're not gonna be able to pull out a ruler and measure and conclude exactly what these are because there's no scale on this picture, right? I don't know. Is 1 inch 1 mile or is 1 inch 100 yards or what's the scale here? So we're not going to be able to get exact about it, but we can see which direction is steeper and which direction is less steep. Yeah. Okay, so notice now we've got 3 very different interpretations of what partial derivatives, I'm going to say, kind of look like, how they manifest, at least, in these 3 different kinds of pictures. And they're very different from each other, and make sure to keep them separated in your minds. Okay, all right. So linear approximations, a couple of quick observations before we get into the meat here. We call these linear approximations even though they're not linear. That's annoying. It's just a terminological point. I'll come back and address that in a moment, but beware, they're not technically linear. The other thing is, I'm going to assume that the linear approximation exists. And it turns out this is a much nastier question in multivariable calculus than it is in single variable calculus. In single variable calculus, the linear approximation, it exists if the function's differentiable. If the function's differentiable, if you can take a derivative, it's really not that much to talk about there, right? I mean, it's just not that much to say. It's much more sophisticated question in multivariable. If I wanted to give a proper treatment, what I consider to be a good enough, anyway, maybe not even proper, but a good enough treatment, take me I think I could do it in a week, but it's a lot. This is deep water, and there's crazy phenomena that happen in multivariable that just there is no single variable analog. So this is a mouthful, but for the moment, I'm going to assume that the linear approximation exists, and then we'll reconsider the question of whether it does or not in a few minutes. Okay, so with that said, linear approximation, y'all remember this formula right here, right? Old news, single variable calculus. I'm sure y'all have seen that formula a million times. Why do we like this formula? What's it good for? Why would we consider this to be somehow relevant? What does it do, right? And different ways to answer that. My favorite way is to say, look, this is the unique degree 1 polynomial that satisfies certain rules. It mimics the value of the function at the point A, and it also mimics the derivative of f at the point A. So this is, again, among degree 1 polynomials, this is the best mimic in these senses, the best mimic of the function f. This is copying f. This is tracking and tracing and, just impersonating f as best as is possible. Because it's got the same value and it's got the same derivative. Everybody buy that? Y'all remember again way back when, and that's what linear approximations are for. Okay, again, there are different ways to think about it. This is the one that I think is going to be most helpful to us. So with that in mind, let's consider now how would I do a multivariable linear approximation. So notice here we've got several input variables, right? Our domain is now Rn. For the moment, we are going to continue to restrict our attention to real values only. We'll talk about vector valued in just a minute. But among real valued multivariable functions, this is the formula that does it. And this is something that you can check. In the same way that you can check that this function has these two properties, likewise, this function here has the same value as f at A, and it has the same, up here we would have said same derivative, but now we've got partial derivatives, and there's a bunch of different partial derivatives, one for each input variable. So this is going to have, in fact, all of the same partial derivatives as f at the point A. And I think this is a great exercise for y'all to think through for yourselves. I would encourage you to start by asking yourself to confirm these two properties for that given function. It's just plug and chug, but make sure you can do this. Make sure you can take this formula for L and confirm that its value and its derivative at the point A agree with F. And then in very, very similar form, you will look at this function and confirm that it's got the same value and the same partial derivatives as F at the point A. Okay, nice little exercise. Now, one little hint I'm going to give you, one thing to keep in mind. Up here, F prime of A, don't forget that that's a constant. It's not F prime of X. Very importantly, not F prime of X. Right, I've got to turn it into a constant by evaluating it at the base point A, and that gives me the necessary, if you will, kind of the, you're going to think of it as the slope, right? But that gives you, that's what makes this formula have the right derivative. So specifically, that's the constant because we've plugged in the constant value A. Likewise, this here is also a constant. And by the way, I'm aware some of y'all might not have seen this notation before. This vertical line here, that's just an alternative way to say the expression on the left, vertical line says I'm going to evaluate it at a point. The subscript is the point where we're evaluating it. Okay. So it's just, in some contexts, it just reads a little better sometimes depending on the situation. So don't forget then, as you're going through and checking these partial derivatives, don't forget that this is a constant. And likewise, of course, so is that also a constant. Okay, great exercise. Give that a try. Let me know if you get stuck. Yes?
Could you repeat the part of the constant? I actually understand.
Yeah, so I'm just saying that, so if you look at F is some complicated formula. If you take the partial of F with respect to xn, that's a different complicated formula, possibly. That's a function. It's not a constant. But this notation here says, okay, well, yeah, but evaluate that function at the point A. A being a fixed point, it's a constant. And when you plug in a constant into some expression, you just get an uglier constant. Yeah, that's all that is. Yeah. Okay. Now, there's a quick little notational observation to make here. Very convenient. See if I can squeeze. Yeah, there we go. Let's look at this. Now, that's not the whole formula for the linear approximation, but it's most of it. Okay? That expression, well, it's a sum of products. The factors in the products are, well, there's a bunch of partial derivatives, and then there's a bunch of, coordinate differences. Okay, it's a sum of products of pairs of factors. Where have we heard that expression before? A sum of products of pairs of factors? That's exactly the structure of a dot product. Right? You can't help but notice that's a dot product. So, in fact, I can rewrite this as a dot product, and it's super convenient and super valuable mathematically to be able to take, long, tedious expressions written in terms of four-function operations and rewriting it in terms of sophisticated operations, because we know cool theorems about, for example, dot products. And now we have a formula that allows us to understand our linear approximation in terms of powerful concepts about which we have tools. So it's not just a matter of shorthand, it's a matter of recognizing an important structure. So now, okay, what are these vectors down here? Well, I think the blue ones are pretty self-evident. Those blue coordinates are literally just the coordinates of the vector x minus a. If you take the vector x with coordinates x1 through xn, and the vector a with coordinates a1 through an, this difference has literally these coordinates. So that part of the dot product is pretty easy to recognize. this other part. What's with all the greens? We don't particularly recognize a vector whose coordinates are apparently the various partial derivatives of f. We've just never, in this class anyway, we've never seen such a thing or done anything with such a thing. So all we have to do is make a definition. I'm going to say, look, here's a new definition. This construction where I have all of the different partial derivatives of some function, I'm going to call that the gradient. I'm going to use this notation. By the way, very importantly, the little triangle here, it has to have the pokey, pointy end has to point down. That's really important. It's got to point down. If it points up, it means something importantly different. Also, that we will talk about in this class, but later on. So anyway, make sure that triangle points down. Otherwise, it's really wrong. Importantly wrong. So yeah, I'm going to define this just so that I can complete this thought and say, hey, this is a dot product, and it's a dot product of things that I can write down. Now that I have the gradient defined, I can literally say that this expression is a dot product of the gradient with the displacement. Okay, is everybody okay with that? All right. A real quick plug and chug. And this is really just plugging in. If I have this function and I want to do a linear approximation at that point, I'm just going to copy off of this formula. And okay, well, first I have to take my function and plug in my given point A, right? So you take that A and plug it into there, and the value of the function is 5. That's just arithmetic. Y'all can check me on that. Okay. Next, I've got to compute the gradient. Now, let's be careful here. The gradient is all of the partials. Here I've computed the partials of f. Now, into that, I plug in my point A. And that gives me then that my gradient evaluated at A is these two values, like so. So that becomes that. And the last thing is the x minus A. So again, you've got to write it down. X minus A is that, and you can see the x has coordinates x and y, and then the A has coordinates 1 and 2. So that's x minus A. And you can, if you feel like it, you can multiply this out. In most cases, there's really no particular need to until you're actually going to be literally cutting wood, right? Or actually programming it into a computer to do 1 trillion calculations. Until you really need to be efficient, in which case, of course, you'd want to multiply it out like this. I think it's fine to just leave it like this. There's no particular need to, Do keep in mind, when you multiply it out in combined terms, you obscure a lot of really useful information, right? It's nice to be able to look at this as written, and I can see the value of the function, I can see the gradient, I can see the base point, I can see that there's a dot product happening. There's a lot of discernible information when you write it like this. That all becomes lost when you multiply it out. Okay. Alrighty. Let's see here. The last thing probably we'll be able to do. Let's extend this to multivariable vector valued functions. Everything on the previous page was for real valued functions. And I could write down the great big formula, and then I could then subsequently come up with a notational convenience, and that just it gets super ugly. So I'm just going to start with the notational convenience because it's super handy. This thing right here is the notational convenience. For the moment, I just want to call it df. There's a reason we use the letter D. I don't want to give you the reason until I can really justify the reason. So I'm not going to say yet what the D stands for, and I'm going to try to restrain myself from inadvertently saying it. So anyway, we're just going to call this DF. Notice DF is a matrix consisting of a bunch of partial derivatives. Notice that they are organized in a very particular way. First column, we're taking the partials with respect to x1. Likewise, second column, partials with respect to x2, et cetera, et cetera. So one thing to keep in mind, columns correspond to input variables that you're taking partials with respect to, not rows. Columns correspond to input variables. Okay. Whereas, by contrast, rows, notice in this row, we're taking partials of F1. In the second row, you're taking partials of F2. Rows, therefore, correspond to output variables. Columns correspond to input variables. Rows correspond to output variables. You've got to be ultra careful to make sure to get the structure of this DF matrix correct. You can't accidentally, whoopsie, my rows became my columns, or and vice versa. You will get a garbage nonsense. It will not do the job that it needs to do if you accidentally transpose it. So I know it seems like a superficial mistake, but it's a hugely catastrophic mistake. So please be very careful. Yeah.
Sorry, what's WLT?
Oh, that's a little abbreviation for with respect to.
Okay.
Yeah. Cool. Okay, so with DF established like that, here's the cool fact. This is the form of the linear approximation, and oh my gosh, it looks so familiar, right? In single variable, this was the derivative that we multiplied by the scalar x minus a. With multivariable real valued, this was a gradient that we dotted with the vector x minus a. Here we have this great big matrix that we matrix multiply by x minus a, right? So the structure of these linear approximations very similar, but they are all different in their ways. So you can confirm for yourselves, and you should, that this again does exactly what it ought to. It mimics f in terms of value and in terms of partial derivatives. I think this is a great thing to check. Don't do this in general because it's just unnecessarily clunky. Just let n equals 3, m equals 2, something like that, right? It'll give you a matrix with 6 entries. You'll have 6 partial derivatives to check. You do the first couple, 3 of them, and you'll see the pattern, and you'll be good, right? So anyway, nevertheless, I think it is a good idea to think through that and make sure, persuade yourself that this is true, that this formula does it. Okay. And again, let's see here. Oh gosh, we're short on time, but you can just let me just kind of wave my hands at this. This formula right here, you can again just plug in. Most of the work of this is evaluating the DF matrix, which comes from first taking the appropriate partials. You got to take all of these. You got to take all the all the coordinates of f and take the partials with respect to all of the input variables, assembled appropriately. Right? Make sure to get that right. Rows correspond to outputs. Columns correspond to inputs. And take the appropriate partials. That's what you get. And then you plug in the point A, and that gets you your matrix. So pretty straightforward plug and chug. And this is a good place to and then my monitor goes out again. Okay, fine. So we'll draw the line right there. See y'all later. If you came in after I did attendance, make sure you come get me to check you off. And give me 2 seconds just to